Okay, here I am again. This time I'm not in Berlin. I'm actually in Calgary, and I'm on my way to Grande Prairie, Alberta for my next flight instructor job at Advanced Aviation. So I'm looking forward to getting up there. It's a nice school. It's got 4 instructors, including myself, 4 Cessna 172s, one with a G1000 package. And there's 2 locations actually, one in Fort St. John, British Columbia, just northwest of Grande Prairie, and the Grande Prairie location. So excited about that. Moving right along, I'm sitting here in a hotel room. I know the lighting is kind of grim, but it is what it is. I have, today's topic is going to be about calculating true altitude and how you might see that question posed perhaps on the exam for your PPL or CPL. And so I have here some notes which I will show you and provide GIFs or JPEGs in the comment section of this video. So what is true altitude? Well, let's talk about the different types of altitude that you could come across in your aviation career. Let's start with the easiest one, the indicated altitude. The indicated altitude is when you set your altimeter setting in the window of your altimeter for the conditions of the location that you're flying over or that you're taking off or landing from. And then what it shows on the altimeter is your indicated altitude. So that's one type of altitude. And then we have pressure altitude, which will factor into these calculations. Pressure altitude is literally the effects of pressure or barometric pressure as measured. So as opposed to indicated altitude, pressure altitude, the best example I can give you is if you set your altimeter to 29.92 or 1013 millibars in the window, then whatever you read off of the altimeter will actually be the pressure altitude. So it's not corrected for the altimeter setting of the area that you're flying over. For example, for those of you flying above 18,000 feet, you automatically set your altimeter to 2992. Now you're reading pressure altitude and you're flying pressure levels. Another type of altitude is altitude above ground. And altitude above ground is the exact distance from the ground in the region that you're flying and where the position of your aircraft is. Commonly, altitudes above ground are calculated, or you can use something like a radar altimeter, which will give you your AGL, or altitude above ground. Now, true altitude is a little bit of a different beast. As you might imply from the term true altitude, it is indicating what the vertical height of your aircraft corrected for temperature and pressure. Okay, and temperature is the key in the true altitude calculation. Now, this is another in the series of my E6b. This is number 2 of my E6b videos. And there you have, I just took the slider part out of the E6b, the nav slider out. And I'm going to show you how to calculate true altitude on your E6b. Those of you who have CX2s and CX6s or CX whatever, the electronic ones, a lot of them, or at least all of them, don't actually allow you the ability to calculate true altitude. Why? I don't know. But the old trusty 70-year, 80-year-old E6b can do that for you. And there's a window designed specifically for it, right over here. All right, altitude correction. Okay, so before we get into using the E6b, I want to talk about the theory behind true altitude and why temperature is so important when you're calculating true altitude. And give you a little bit of an example of why it's an important thing. You may remember from ground school class, if you have gone to ground school class, the concept of columns of air. All right, imagine a big test tube full of air. That would be a column of air extending from the ground all the way up to the edge of the atmosphere. Another real-world example of a column of air is a pressure system. Okay, a pressure and temperature system, highs and lows. Systems that move from one part of the region into another part of the region, bringing the characteristics along with them, could be considered like a column of air. So here you can see, in this diagram here, I have three columns of air drawn out. Okay? I have in the center, I have what we call the standard atmosphere. Then to the left, I have the warmer atmosphere. And to the right, I have an example of a colder atmosphere. Okay, so this will factor into the true altitude calculations. All right? And you can see warmer, standard, colder. All right? The little dots in the columns of air represent air molecules. Okay, and you can see that the distribution of the air molecules between the warmer than, standard, and colder than temperature air have different distributions of the molecules. Most specifically, at the bottom, you can see the difference. You can see that all of the molecules are jammed pretty close together at the bottom of the colder air mass, whereas they are distributed less densely at the bottom of the standard air mass, and they are actually distributed wider apart in the warmer than standard air mass. So that should give you a clue of what's going on there. Essentially, without getting into advanced physics, which I am not an expert in, essentially what's happening in these different columns of air is that the weight of the air is affected by the temperature. Okay? So less excited molecules, in other words, molecules that are not warmed as much, will congregate together and sink to the bottom, compressing. Okay? And then as you go higher and higher and higher towards the edge of the atmosphere, as the atmosphere thins out, these molecules become less and less and hence appear to be more spread out. But the key here, and you can see it right here in the diagram, is that in the standard column of air, you can see that the molecules at the bottom are in fact compressed more together, and then they start to spread out, and there's more space between them as you go higher and higher to the edge of space. You can see here in the colder column of air that the weight of that column of air, because of the coldness, compresses all of the molecules towards the bottom or the Earth level of the atmosphere, but yet they also spread out as you go higher and higher and higher towards the edge of the atmosphere. You can also see in this diagram here that the warmer column of air automatically has a less dense packing of the molecules at the lower levels, but does in fact spread out more space in between the molecules, again, just like the other two columns of air as you reach the edge of space. So there's your clue, okay? The colder air molecules settle lower, but the distribution or the graduation of more and more space between the molecules remains the same as the standard column of air and even as the warmer column of air. So what does that mean? Well, how does an altimeter work? An altimeter is just simply a barometer, okay? So it senses the density or the pressure caused by the air molecules. So if you're at a lower level where the molecules are closer together, they exert more pressure on the altimeter and then will actually make the altimeter read a lower altitude. And as you go higher, there are less air molecules exerting less pressure on the bellows of the altimeter, and it will accordingly indicate a higher altitude. So that's the key here, okay? So imagine you're at an airplane and you're flying along at 10,000 feet indicated altitude. Okay, that's what your altimeter is showing you, 10,000 feet. So that means that for an altimeter to be set at 10,000 feet, there has to be a certain amount of molecules in the air exerting pressure on the bellows to put the needle exactly at 10,000 feet. And that's what the pilot sees. But you can see in the diagram that the pilot that's flying in the warmer mass of air experiences the same density of air molecules as the pilot flying in the standard temperature column of air and as the pilot flying in the colder than standard temperature column of air. Now, standard temperature is based on 15 degrees Celsius at sea level, And then accordingly, 2 degrees or 1.98 degrees Celsius per 1,000 feet will the temperature drop. Okay, so this would be that standard model. Okay, now it is true that the temperature will also decrease at 2 degrees per 1,000 feet in the other columns of air, but because of the distribution and the weight of the molecules of the air in these different columns, even though each of these airplanes are experiencing 10,000 feet of pressure altitude in their indicated altimeter, they are in fact flying above the ground at different heights. There's the 10,000 feet, so let's imagine 10,000 is 10,000. But in the warmer air, even though the altimeter is indicating 10,000 because of the distribution of the molecules and the less weight of the colder air, or the warmer air, that airplane is in fact flying higher true altitude. And conversely, with the more densely packed column of air, because of the weight of the cold air, even though he's reading 10,000 feet indicated, he is in fact, his true altitude is considerably lower than the standard temperature aircraft that's indicating 10,000 feet. All right, so that's the basically big picture behind what we're doing. What we're trying to figure out in this calculation is really how high above an obstacle or above the ground are these airplanes all indicating the same 10,000 feet. Okay, so that's what we're up to. So now we have the calculation side here. So typically on the exam, you'll get a question that's modeled more or less like what I have here. It's going to give you some information that you need for your calculation. Can you imagine what that information is? Well, yes, temperature. Okay, what is the indicated outside air temperature as you're flying along? That's one thing you need to know. Another thing you need to know is the pressure altitude. In other words, what is the actual pressure altitude as opposed to the indicated altitude? Okay, so you're going to have to figure out the pressure altitude. So that's very important. All right, and then the third piece of information will be some sort of an obstacle clearance. All right, it indicates that you're at, say, for example, well, let's just get right into it. I have 3 examples here. Okay. In the first example, we have outside air temperature plus 23 degrees Celsius. Outside air temperature plus 23 degrees Celsius. In the second example, I have outside air temperature reading minus 30 degrees Celsius, considerably cooler. And the third one, the outside temperature would be plus 30 degrees Celsius, so that's considerably warmer. All right, so we need to calculate the pressure altitude, and we have the temperatures, and we need to apply the correction using the E6b. All right, and then we will know what our correct clearance is. Well, what do we mean by that? We'll have a look at this diagram here. Here's a reporting station, say an airport at sea level. All right, and here is a hill or a mountain at 3,500 feet of AGL with respect to 3,500 feet ASL with respect to sea level. Okay, so that's going to be factored into your clearance. All right, and then you have your airplane here, and the airplane is going to be at the same indicated altitude for each of these 3 examples, and the air altitude is 4,000 feet MSL. 4,000 feet MSL. And this mountain is 3,500 feet above ground level compared to the airport that's reporting altimeter information. All right, if that's at sea level, then that's also 3,500 feet ASL, or mean sea level, depending on which term you want to use. So the question is, if you're flying along with an indicated altitude of 4,000 feet MSL, all right, in these 3 different temperature columns of air that could be existing over this scenario, what is your actual clearance over a 3,500 foot mountain? All right, are you going to cross the mountain safely? Are you going to just skim it, or would you hit the side of the mountain, even though at first glance it seems to be 1,000 feet below your aircraft? which is indicating 4,500 ASL. So we'll start with the first one. Outside air temperature is plus 23 degrees Celsius. All right. The altimeter setting, the reporting from the station, is 29.92. Those of you who know how to calculate pressure altitude would know that 2992 altimeter setting will require no correction between your indicated altitude and your pressure altitude. I just set it that for simplicity's sake. If the altimeter setting was higher, well, then there would be correction, and the airplane would actually be flying lower than indicated in terms of pressure altitude. And if the altimeter setting was lower, with thinner air, then the airplane would actually be flying higher than indicated in terms of pressure altitude. All right, but I just, for simplicity's sake, set that at 29.92 at the reporting station. All right, so what we need to, and just to remind you, there's two basic ways to calculate pressure altitude. One is simply make a note of what your altimeter setting is for future reference. Turn the dial until it's set to 2992 or 1013 millibars, and then read the altimeter. That'll be your pressure altitude. The second method is to take 29.92, all right, and then subtract the altimeter setting, and then the difference will be applied to your indicated altitude. If it's a negative difference, then the difference would subtract, and if it's a positive difference, then the difference would add, and that would be your pressure altitude. So, for example, at 1,000 feet, say the local pressure is 3092. So that's 1 full inch higher than 2992. Then that would be 2992 minus 3092 would equal minus 1.0 times 1,000 is minus 1,000 feet. Okay? So that's how you would calculate your pressure altitude. And so I have the little equation right there. Standard, and this, in our case, because the altimeter setting is 2992, so 2992 minus 2992 equals 0, which means we need not correct our indicated altitude for our pressure altitudes. They're the same. I just did that for simplicity's sake. So let's take that first example of 23 degrees Celsius. Well, you use the altitude correcting side of the E6b on my particular model, which is a 1992 model. You can see it's on the left-hand side. So in the window, you're going to see two sets of measurements. Inside the window is the air temperature in degrees Celsius. So going from 0 in the positive direction and from 0 in the negative direction. And then just outside that window is the pressure altitude in thousands of feet. Okay, so we have done the pressure altitude calculation. Okay, in the case of the altimeter setting being 2992, then the indicated altitude is essentially the pressure altitude. So we have an indicated altitude of 4,000 feet. I think it's earlier I said 4,500, but it's actually 4,000 feet. Indicated at 2992, it's going to be the same pressure altitude. Okay, just try that on your own when you're sitting in a plane some morning. And you can see it works quite well, or do the calculation at home. Okay, so that means we need to take that 4,000 feet, so on this part of the window, and line it up with the temperature of 23 degrees Celsius inside the window. So I'm just going to do that right now. So 23 to 4,000 feet, and they are lined up, 23 and 4,000 feet. So you can see there's my 2, 4, and 23 degrees Celsius, plus 23 degrees Celsius. Just double check, make sure I'm not fooling myself, and that is correct. 4,000 feet on 23. All right, it's not a super exact gradation. There's a lot of room for wiggle in there, a little bit here and there, but you'll get the idea, and you'll get it right in the exam if you use your E6b, because they'll make the range of answers far enough away that tiny little movement error, because of just simply how close together the different thousands of feet are, will give you the correct answer in the exam. So here we go, all right? So that means now that you would use, and it says right here, set pressure altitude opposite temperature, read true altitude on the outer scale, opposed to the indicated altitude on the inner scale. So our indicated altitude is 4,000 MSL, so I simply look for 4,000, pardon my E6b is a little bit old and some of the ink is rubbing off. There's 4,000, and when I look on the outside ring, it's 4,200 feet. 4,000 lines up to 4,200 feet. You can see right there. Okay, so that means my true altitude is in fact 4,200 feet. So that's 200 feet higher than indicated. So that would indicate that I'm going to clear the 3,500 ASL mountain by 800 feet. 4,700, let me just double check what we got there. 4,000, yeah, 4,200, so 35, yeah, 700 feet. So good clearance there. So in actual fact, the airplane is going to go over this mountain without obstructing terrain. Now let's just switch to the minus 30. The minus 30 outside air temperature. Now this is the air temperature that you're getting while looking at the air temperature gauge in flight. So again, we have 4,000 feet indicated. Now we're setting it against minus 30 in the E6b. So I'll just set it and then show it to you. Minus 30, 2, 4. So here you can see that there's minus 30 set against 2, 4. All right. So on the inner scale, we're going to look for the 4,000 feet again, and there's 4 there, 4,000 feet, and look at that. The 4,000 foot mark is at 3,400 feet. So, no, we're not going to clear the 3,500 foot mountain. We are in the scenario of colder than normal, colder than standard column of air. So what's happened is the airplane is actually lower than in the previous calculation we did, which was pretty close to standard temperature. So as you can see, at that height, a 3,500 foot mountain, and your true altitude is actually 3,400 feet, the aircraft will impact the terrain. Okay, there you go. Let's try one more. We'll use the warmer than standard air temperature. So in the warmer than standard air temperature scenario, we have an outside air temperature of 30 degrees Celsius. So 30 degrees Celsius goes against 4,000 indicated or 4,000 pressure altitude because of the altimeter setting being 2992. So there's 2, 4, 30 degrees Celsius. That's pretty warm up there at 4,000 feet. That's very warm. Okay, now we'll look at 4,000 feet. There's the 4,000 foot level, and you can see we are at, in actual fact, 4,100, 4,200, 4,300, 4,400, 4,300 feet. Okay, so that's quite a bit of clearance. So this airplane, its true altitude is actually it's 900 feet higher than the top of the mountain. Okay, so that would be the warmer than standard temperature column of air. And as you can see, clearly indicated, even though each one of these airplanes is reading the same indicated altitude, they are in fact at different heights above the ground. Okay, so that 3,500 foot mountain, okay, you're safe with the 23 degrees Celsius outside air temperature and the 30 degrees Celsius outside air temperature. But once that air starts getting cold, like minus 30, the airplane, even though it's reading 4,000 indicated, is in fact lower than the top of the mountain. So you can see why true altitude is an important calculation to have. If you look at the upper air charts, the pressure level charts, you will see that, especially on the 10,000 MSL chart, which is the 400 millibar chart, 700 millibar chart, you will see areas of equal temperature are connected by lines. And imagine all of those airplanes flying above 18,000 feet, they're all flying with their altimeter set to 2992 because they're not in the altimeter setting region, they're in the standard pressure region. All of those airplanes, as they go through together, say two airplanes are both at 20,000 indicated, one behind another. As they go through the different regions of air, which are colder and warmer, together, their true altitudes are going up and down as they go through these different columns of air. So in actual fact, even though the airplanes are reading the same indicated altitude, they're actually doing a little dance together as they go up and down in true altitude as they navigate to their destination. Pretty cool, huh? So there you go. That's my quick little demonstration on using the E6b to calculate true altitude. Remember again, I'm pretty sure the CX series of electronic E6bs do not give you that calculation. Why? I don't know, but this does. So it's very handy to have during your exam. You get a true altitude correction. It's going to usually be involved of you think you're flying at this altitude, and the pressure is, the altimeter setting is this, and the air temperature is this. What is your clearance from an obstacle? That's usually the way the question is framed. And if you check your instructions on the E6b, there's a series of example questions that you can go through and check your work against. So there you go. Once again, the E6b reigns. So that's it for today. I hope you have a great day wherever you are. I'm looking forward to getting back in the airplane again up in Grand Prairie, Alberta. And I'll see you again on another Mayday flight tutoring video. Bye for now.